past week to 10 days, it's been like quantum week. There's a lot of news coming out of that sector.
Absolutely. I see quantum computing as the new class of accelerator.
From Orion X in association with Inside HPC, this is the At HPC podcast. Join Shaheen Khan and Doug Black as they discuss supercomputing technologies and the applications, markets, and policies that shape them. Thank you for being with us.
Hey Shaheen, great to be with you again.
Great to be with you, Doug. How are you?
Good. So past week to 10 days, it's been like quantum week. There's a lot of news coming out of that sector.
Every day, a few non-trivially important, at least the dollar amounts.
And overall, we're looking at several themes that seem to be coming to the fore. There are four main themes. We're seeing obviously overall R&D work, so announcements from various startups and bigger companies about progress just being generally made based on their quantum strategies. And you frequently see we're moving toward quantum superiority. Quantum error correction is a huge problem that's the focus of a lot of work. Several companies that are working on melding quantum and classical. It's sort of a bridge to quantum that utilizes computing techniques that are already well established and people are familiar with. And finally, there's just a lot of money being poured in to quantum from venture capital and other investment sources.
Yeah, I want to add a couple of other categories. One is partnerships and M&A. Of course, we had the big one with Honeywell and Cambridge Quantum Computing last year, and this week saw some additional partnerships that were announced. And then the other one is the quantum computing HPC connection that I think will increasingly be felt. There was news that Jülich now has a D-Wave system as part of their supercomputing facility, and there will be others that will be doing that.
To my mind, the thing about quantum is it fits into my overall general sense about high-end computing broadly defined. In so many of these areas, if it's quantum or data science and AI, it's becoming so rarefied. And the skills and talent required to be an expert in these areas and to be actively pushing forward the technology it's just at otherworldly level. I almost see this cadre of very top level people that are just at a whole different level from the rest of us.
Yeah, you're right. My own joke is that the voodoo factor in quantum computing is still off the charts. But I think we can all take some solace in the quote from Richard Feynman that said, it's attributed to him. I think you brought it up last time, that if you think you understand quantum mechanics, you don't. I don't think he actually said that, but nevertheless exemplifies that even people like him had difficulty understanding this. So, maybe we can be forgiven for not quite getting it.
Well, I've written a bit about data science, but quantum is data science on steroids in terms of complexity and its removal from the comprehension of most people. But, being in the technology industry for decades now, we all know the experience of kind of nodding your head as though you understand what's being said in whatever the discussion might be when you actually don't. But when it comes to quantum, it's just ridiculous. I once saw a great presentation by Kevin Kissel. He's heading a lot of the quantum work going on at Google, a really brilliant guy. And he gave a great presentation in which he said the reason quantum is so hard to understand is that everything that happens is happening at the atomic and subatomic level. So if you've mastered the atomic level, you still have to go to the subatomic level. And that the way things happen at that realm of existence is completely unlike what we're used to in the world that we've experienced. So there's no frame of reference for us.
Yeah, right on. My take is that that's kind of okay. And I rationalize it by saying that it's just early days in quantum computing. Because if you look at traditional computing, it's not like everybody knows what happens at the bit level down in the silicon and what sort of quantum effects might even exist there. And they do increasingly. All you know is that you say A equals A plus 1 and it happens. And you don't really need to know how it happens. And we haven't got to that point yet in quantum computing where you have a group of people who really understand what's going on at the technology level, but then that is abstracted by multiple layers on top until you get to average users who really don't need to know what's going on under the hood, but they know that if they do this, that will happen. And we haven't quite got to that point yet.
All that's true. But if you take, for example, one of the stories this week is that Atom Computing just raised $60 million in a Series B round. Whenever I see a story like that, I really wonder how much the folks making those investments really understand what they're investing in,
Well, I think folks who are making those investments want a seat at the table. They know that this is a really significant wave of technology. They know that something is going to make it happen. There is increasing consensus that quantum computing will work one way or another, that if it doesn't, we're going to have to rewrite some laws of physics to figure out why. And there is increasing evidence that some applications are starting to become reality. So people want a seat at the table and they're willing to buy that seat. So I think that's really quite legit. It's okay. Now, it's true that because quantum computing is so early and there are so many different paths to achieving quantum computing, I mean, you're trying to really control quantum effects. And where do quantum effects happen? Well, they happen everywhere. So in principle, you could attempt to control it in many different ways. And we are seeing that. So you see ions, electrons, atoms, photons, all being subject to
diamonds.
Exactly. How can I isolate it? How can I control it? Quantum computing, like he was saying, is all probabilistic and we don't really, on a day-to-day basis, live in such a world. So how can I control those probabilistic functions? And therefore you get all these different ways of doing it, right?
As you say, there's so many different routes to so great a possibility of computing. It's almost a global crowdsourcing effort. It's going on everywhere, and people are taking different approaches.
Right. I liken it to traditional computing before the transistor. And I think we have not reached our transistor moment when one technology is going to establish itself as the horse to bet on, and then you just catapult into the future.
Yeah.
Or, VHS Betamax. It doesn't have to be the best one. It just needs to be the one that gathers steam and works more often than not.
Yeah, that's an interesting point. And you wonder about the patience, how long we will be patient with the development in quantum. I know, for example, IBM last May said they will deliver an 1100 qubit IBM Quantum Condor chip by next year. I mean, that's closing in. Yet, one of the announcements this past week is a IBM quantum simulation technique called entanglement forging, which they say basically allows you to do twice as much with the same number of qubits. But they're doing it on a Falcon quantum chip that has, I believe, 27 qubits. So
right, they've been really executing well. They've been meeting the objectives that they put on, and they've, in general, have done a marvelous job in their quantum computing effort. But if you look at what you need to really execute, you need the number of qubits, and you need those qubits to have high fidelity, low noise, and you need to be able to connect many of them together. The more the merrier, and I think this entanglement forging does that, to create a bigger circuit size, right? Now, at the moment, the industry calls itself in a zone called NISQ, for noisy intermediate scale quantum computing, where the number of qubits isn't quite as large and they're a little too noisy, and it's more of a proof of concept and an occasional application or a kernel that does really well in terms of competitive advantage. But the perception is that you need a lot of qubits to really get to actual applications that are beating traditional computers. So depending on the path you're taking, hundreds or thousands of qubits are necessary. So they're on that path, and more power to them. I hope that they stay on the schedule that they've laid out.
For myself, overall, long term, I'm optimistic. Quantum will get to commercial viability. There will be quantum advantage.
Right.
What scares me a little bit is putting out these hard and fast roadmap deadlines. Next year for an 1100 qubit chip. It's kind of like, Intel saying they're going to get to zettascale by 2027, and a journalist said, you might want to add a year to that. Oh, okay.
I think the zettascale stuff is a little bit more conceptual and aspirational, and really nobody's taking that as a roadmap. I think the quantum computing roadmap that IBM laid out is a lot more achievable, and within their existing norms, I think they can do it.
Okay.
But you're right. It's a nice parallel to know where HPC is going to get to, where it's going next, and where quantum computing. And of course, HPC and quantum are joined at the hip anyway. And I'm really excited to see what Jülich does and what other supercomputer centers do. Obviously, Los Alamos and NASA did a brilliant quantum computing workshop at SC21.
Mhm.
And Sandia was in the news with their tomography process that seems really, really nice and works well.
Gateshead tomography, yeah,
Gateshead tomography, that's right.
Diagnostics
Right.
technique.
That's also a reminder that the whole industry is morphing into quantum sensing for measurements, quantum communication, which has been around for a long time, quantum effects at least have been, and then quantum computing. So those are three market segments within the quantum information science umbrella.
My hat's off to these companies that are doing this quantum classical bridging. For example, Multiverse, which is based in Spain, doing this stock valuation calculation capability, but the front end of it is you use PC plugins. They're trying to get around, that you need any kind of quantum skills or knowledge to hopefully leverage this capability.
Right. So the applications for quantum computing, if you think of it fundamentally, what can I do? Well, you could do quantum science because, well, it's quantum and it lends itself to quantum computing. So I expect quantum chemistry, quantum physics kind of applications to emerge. And there's a lot of activity to get those going. And in fact, the IBM application included simulation of the water molecule, which is very, very important because it shows up in all sorts of biological systems as well. And water is a especially complicated molecule because of its electrochemical qualities. The next one is optimization, and digital annealers and quantum annealers like D-Wave have been showing the way there. You can take those two and apply it to a lot of different applications. Then there is quantum machine learning, and that has been getting a lot of attention over the past couple of few years. If you get those three, you can get the combination to now claim applications in other areas that aren't obvious. The metaverse one is a little bit more out there. It needs to be explained exactly how these basic building blocks of optimization, quantum, and machine learning are being applied. But it could be, yeah.
Yeah, and the current expectation, of course, is that quantum applications will be very specialized and defined, and that quantum systems will sit alongside HPC classical systems, taking on those specialized workloads.
Absolutely. I see quantum computing as the new class of accelerator.
Right. So I guess maybe the expectation is we'll just start to see the lineup of those quantum workloads that can actually be executed filling in the coming years.
Yeah, that is really my wish. My wish is that these applications that are being pursued, hopefully the companies doing them can share a lot of information so that we can feel the realness of it. Because right now, when I read the press releases, it's hard to tell how real it is.
Yeah, we're looking for more proof points.
We are. And I think the moment something like really real happens, that may just get us closer to that transistor moment.
All right, Shaheen. Well, as always, great to be with you, and we'll talk again soon.
On that hopeful note.
On that hopeful note, exactly.
All right. Take care, Doug. Thank you.
Thank you. Bye.
That's it for this episode of the At HPC podcast. Every episode is featured on InsideHPC.com and posted on OrionX.net. Use the comment section or tweet us with any questions or to propose topics of discussion. If you like the show, rate and review it on Apple Podcasts or wherever you listen. The At HPC podcast is a production of OrionX in association with Inside HPC. Thank you for listening.